Hello everyone and welcome to our final closeout video on UPLC converter. So as the result of our final milestone and of the whole project, we prepared an CLI app, which I'm going to demonstrate right now. It's available at our repository called zkfold Cardano as a target called zkfold UPLC converter. It is built using Cabal. I've just prepared it in advance not to waste any time on building it. And well, let's run it and see what it has to offer us. Yeah, so that's the standard CLI app. It supports your usual options, including help, feeding some binary input and producing output, and so on. Yeah, so to start with the input, you can either specify like the kind of input you feed via standard input. So we support all the types of inputs which are supported by the standard Plutus CLI, including both untyped and typed Plutus core dialect, then the Plutus intermediate representation, and different encoded formats of UPLC, UPLC flat, and UPLC CBOR. And just as well, you can feed one or more file names as positional arguments, just like to specify the input. And then the type of input would be inferred deduced from the extension of the file. You can specify just as well the version of the contract, which we are going to convert into arithmetic circuit. We support both the latest version of contracts, the v version 3 contracts on Cardano blockchain, and spending contracts and other kinds of version 1 contracts, which are meeting, certifying, and rewarding scripts. Yeah, and about the output. By default, we're going to produce the circuit and just write it to the standard output, the arithmetic circuit, which is the result of the conversion of the smart contract. But just as well, we have more options available. So we can also print the prover info. So the program runs the prover setup and outputs the prover info. Or you can just as well generate the Cardano smart contract, which runs the PlonCap verifier for the circuit, and when output it in the compressed CBOR format. Let's see how it works. So by default, the converter runs on the standard input. So here's, for example, a simple contract which outputs its own input. It's not correct because, by the specification, the output should be unit for V3 contracts. But for now, we allow this just for simplicity. Yeah, and that's it. And the output is a constant circuit which always outputs 1. This means that the circuit ran successfully. It is the encoding of the true value. So the output is some kind of a Boolean, and here it outputted true, which means that like the computation is okay. So that's for the as I said, the input can be fed via feeding like the files directly, and that's the identical input. This is the one I've written out explicitly. Yeah, and for some more options, we can also print, as I said, the prover info. Yeah, so the prover info are some quite a bit of different vectors and polynomials in the BLS scalar finite field. We don't have to look too much into it, and that's just like the info we use for our prover on top of the PlonCap algorithm we have. Also, we can also print the verifier. It's not going to print like the script itself. It's already packed that it's the V3 Plutus script with the following hex encoding. And here in this hex, we have encoded the verifier for this specific arithmetic circuit. Just to take a look at some more examples, we have some of the more trivial programs. So for example, the cont true one just runs the if then else conditional on the constant true value. If it's true, we complete the smart contract successfully. Otherwise, we terminate with an error. So let's see what the output. Can you guess what it is for like this circuit? Yeah, it once again is just the truth. Just the true. We after performing symbolic computation, we can see that like never mind the input, it always outputs the unit without any error. We have sibling smart contract, which is if then else, but now it's run always on false, and it returns an error on false. Let's see the output. Yeah, here it's 0 because we like finish the execution with an error, and so that's what gets encoded here. And for a non-trivial example, let's take a look at the one I called points. So this one is performing two if then else checks. If either of them is not true, if the result is not true, it terminates with an error. So first it checks for equality of these two integers. So you can guess that this should return true. And then we check equality of byte strings of this one, the constant byte string, and the data we get from the input. So of course, on real blockchain, it's going to end in an error because the X fed into V3 contracts is not just a byte string, it's some other more complex object. But just for demonstration purposes, yeah, we just run this built-in, we get the byte string data and then compare the equality. So let's see what happens on this example. It's going to take a while because like the produced circuit is going to be quite big, because like well, this one is going to be optimized away because like these are two constants, and constants are represented trivially in the circuit. Yeah, so here's the output. So this one is from comparing two byte strings. Why there are so many different data and constraints? Well, that's because we have huge byte strings which are going to be compared, and this is not a fast operation in arithmetic circuits. It requires quite a bit of data, so that's what's being fed into the output. Yeah, so that's it about like the demonstration. Let's go over the general architecture. So the first of all, the entry point to our CLI app is a usual opt-parse applicative application. We parse the command line options, which we showed. We have many of them. Then we convert the input to a single UPLC program, which we then reparse using the megaparsec parser. And then the parsed term is fed into our conversion pipeline. And then when we get the circuit, if the output is specified, we feed the circuit to the output, and then write down different setups for the setup for the prover and the setup for the verifier. Yeah, and for the verifier, we must remember that we encode not just the setup, but the verifier itself, already compiled and packed into binary representation. So that's like the general outline of the architecture. I'm not going to go into details too much, just to remind you how this actually this conversion algorithm happens. What's going on? It's defined not here. It's defined in our core repository, which contains the core definitions. It's called symbolic. So it has some library code devoted to the UPLC converter. So what do we have here? Aside from the definition of different UPLC primitive, just different specification for built-in functions, types, contents, data, and what is UPLC term. So we define what is the UPLC conversion procedure. It's defined in the symbolic part. Yeah, so let's see. So the converter itself sorry, just chooses an appropriate type of the script, then feeds appropriate inputs into the contract, and then runs the conversion itself. The conversion is actually just the symbolic evaluation of a UPLC term. The algorithm should be understandable for the ones who are familiar with lambda calculus and so on, and stuff like this. So we just evaluate the lambda term of UPLC calculus. But there's one difference, that instead of evaluating in terms of lambda calculus, we evaluate in terms of these the symbolic values that we have, and then match on the result whether it's it computed successfully. Yeah, so that's the gist of the general converter algorithm. And let's move on to outlining which challenges did we have while implementing this converter. Because there was a few, and just to name some, which problems did we have? Not problems, but challenges. So the first challenge was to actually create some working documentation on the converter which we are going to have. It's already available at our documentation website. Yeah, so here it is. Just an outline of what is done in the UPLC converter, but nonetheless. Yeah, then we had to implement a prototype for a limited subset of UPLC. So this work was done in this core symbolic repository. We defined some library code just to how to perform this conversion. Yeah. Then we added the circuit generation for basic built-in operations. It can be looked up in this evaluation module. Yeah, so here we have dedicated functions called apply poly, which apply polymorphic built-in functions, and eval mono, which evaluate the monomorphic functions of UPLC. And we have a few. Yeah, we have them. Then the circuit generation for more complex built-in operations. So once again, we needed to support some of the cryptographic primitives, some of the operations on the BLS curve, and then finish up with the CLI tool prototype with the core functionality. Now, to reiterate once again, it's available at the zkfold Cardano repository under target code zkfold UPLC converter. Yeah. So then, just to sum up what we did. So we now have a functional UPLC to ZK circuit conversion, which, as we have seen, performs basic conversion for UPLC contracts, for contracts written in the UPLC language. So we have added the support for both basic and complex built-in operations. We devised a CLI tool for developer usability. We added documentation for the developer onboarding. We added some test coverage and reliability. So there are some basic tests. They're once again in the library code. So what happens is we have some unit tests for several just UPLC programs, just like the ones we've seen before, just embedded in our representation of UPLC. Yeah, why do we have just unit tests? Because it's hard to come up with the proper properties for property-based testing. So instead of that, we just test for some specific contracts and see if they work. Yeah, so this is ready for integration with other language tool chains. You just need to have the Bluetooth CLI installed as well, and the UPLC converter CLI compiled and installed as well. And then you just run the converter on the outputs which are supported by the Bluetooth CLI, and you're good to go. And all modularity, and of course, all this architecture is modular and extensible, because it's like it has several layers. So first of all, this all is built on top of our symbolic DSL, which defines the basic domain-specific language for compiling and running arithmetic circuits, which are primitive for zero-knowledge computation. Then we define we formalize a part of the UPLC spec in our symbolic UPLC library target, which is then used by the ZK-fold UPLC converter binary target, which ties it all together in a single application. Yeah. So just to sum it up, to take a look at key achievements. So we delivered a working UPLC to ZK circuit converter, arithmetic circuits for full built-in coverage. We built a CLI tool integrating core ZK workflow, and we established an integration path for all Cardano language toolchains. Yeah, so that's it. You can find more info in our closeout report in a PDF. But I think with this video, we are done. Thank you for your time. Thank you for sticking with us. Look forward to more updates from our team.